Hello, so welcome back to dark matter and dark energy. This is kind of the follow-up of last time's program with Gloria and Ethan. First, I want to apologize for the format where we presented it, and now watching it again, I think Gloria is kind of rude and interrupting all the time, and a little bit annoying, but they're kids, so short attention span, and they don't have, deep thoughts. Anyway, let's go back to, so basically I want to explain what I revealed to them in a more adult manner. And I want to look at the biggest discoveries of the 21st century. Some may say is the black hole picture, or the gravitational waves that we measured a few years ago, or the Higgs boson that was discovered or confirmed at CERN also a few years ago. But as it's still, I think overall, dark energy and dark matter, actually dark matter was discovered a long time ago, or the trace of it, or the evidence for it. But dark energy is pretty much in the 2000, early, or 1999, somewhere around there, when I first entered college. Anyhow, those are the big topics, still unknown. Things up here, we already know. It's just experimentally we have confirmed these theories. They're great work. Don't get me wrong. They're Nobel Prize worthy. So, but these things are truly going to expand our understanding of the universe, because they are more of a universe than we can see right now. Okay, so without getting into too much of the earlier or simpler physics, let's look at what dark matter is and what we know about it. So, other than gravity, dark matter hasn't been detected to interact in any other way, right? So basically, we have these gravity lensing we see, and then we also detect all the movements of the stars in the galaxies and figure that they can't possibly be moving that fast without a stronger gravity to hold them toward the center. Also, there's, let me get that out of the way. There's the microwave background survey that we've done recently that shows the early imprints of the universe. And it appears that there's places that are more empty, and then there are places that are more massive from the get-go of the Big Bang. So that's how we end up with the universe as we know it. Anyway, so these are the evidences for the dark matter, but not much more. Let's look at dark energy. What we know so far, for sure, right? We know the Big Bang theory. I don't want to repeat that, anything like that. And then Einstein has a big blunder of cosmological constant, that's keeping everything suspended in the space, right? So not all the stars and galaxies, they don't collapse together due to gravity, because there's this constant that he imagined. He called it his biggest blunder. But it turned out that he was right all along, that there was this mysterious force. Some physicists described it as the negative pressure of space. So, we all understand positive pressure. Negative pressure is sort of, if you are, imagine, the movies where people were exposed into space, and then their internal pressure of blood and everything is higher than the empty space outside, so they explode, sort of. So that's sort of the negative pressure, but the space is already very empty, and then it has this energy of negative pressure to stretch it further. Okay, so that's how we describe dark energy. And it's also growing faster. The current rate of expansion is about 78 to 80 megameters, so million meters per hour per light year. So every light year we're expanding at this space speed. So that's what we know so far. The Hubble. This is also the Hubble constant, or the Einstein's cosmological constant, or something like that. So this is the measurement right now. And what we discovered at the turn of the century is that it's going faster for some reason. That's what we describe as the dark energy. And it's pretty much confirmed, because multiple studies and measurements have confirmed that. Anyhow, so this is my thoughts on the dark energy. Space-time, as the fabric of the universe, has a spring constant. So that's how I explain it. People usually describe the expansion of the universe as a balloon, right? You're blowing up the balloon, and the balloon inflates, and stuff on the surface of the balloon sort of move apart from one another. But intuitively, the balloon tries to push the air inside out, okay? Because the material has a certain flexibility, and its ground state is a sort of like a small state, right? It's a small volume state where there's no air inside. And when the balloon is pumped in, the air pressure is added in, then it sort of expands. But my thinking is that the space-time itself could be just like a balloon, except that the balloon, the surface, every part of the surface of the balloon wants to be flat. And the net result is that it cannot be flat totally and retain its continuity, right? The only way it's going to approach flatness is through expanding. And then that gives this kind of negative pressure or the springiness to this expansion. Okay, so it is fairly simple to model mathematically. It's very similar to a material. So if you ask a civil engineer, and they know all about it, and then to have just basically treat space-time as a material, okay, and it has a certain springiness, flexibility into it, and it has certain amount of sort of elasticity in the material itself. But this material is four-dimensional, okay, and then the Hubble's constant is not really a constant. It can be defined with a differential equation of some sort. The force of expansion, or whatever the rate of expansion, can be a function of the curl of the space-time, right? I know that we're thinking that the space-time, well, the measurements that we have of the space-time is by large really flat, okay? But then I think it's misleading. The universe is already really flat already. It's true on a certain extent because the universe is so vast, it's so big, right? So it's pretty much flat wherever we look. But however, the observable universe is so small right now compared to the whole universe that on a larger scale, I do believe that the universe is not flat; it's curved somehow, and that curve gives the spring constant a little bit of force to expand it even further, and it's never going to be flat after all. Even so, that goes into the dilemma whether the universe is infinite or finite. My belief is finite, but then there's no way to prove or disapprove that it is. My thought is that if it's infinite, if the universe is infinite, right, it has to start out with infinity. It has to start out, infinitely. Okay, we can't have like a finite egg and then just explodes and the Big Bang grows into an infinite something within a finite amount of time, right? So even if it is infinite, right, whatever we can observe ever from any point in the universe, for example, right now on Earth, right, or anywhere in the history of Earth, or wherever, any point in the history, so that is still finite, right? Beyond a certain point, it's non-observable. We already know that. Just mathematically impossible, unless you go beyond speed of light. That's entirely something else. So let's not go there yet. But let's just treat the universe as a finite entity, right? But then it's approaching infinity. You're trying to approach flatness. The flatness, that's what gives the dark energy its drive, right? So that's my take on the dark energy. So we don't need to. Okay, we'll talk about implications later on. And dark matter, space-time is not perfectly flat, smooth on all scales, okay? So what it is that space-time, by large, the whole universe wants to be flat. But on a smaller scale, like a galactic scale, and on the clusters and superclusters and then these kind of groups, they sort of are not smooth or flat, okay? So some of the space-time just sort of wrinkles itself. I have this little poster of a movie, A Wrinkle in Time. Okay, I didn't watch that movie, but that was something even Hollywood can think of, that time can wrinkle. Certainly space-time can wrinkle. Right? Space-time is wrinkled by mass. That's the whole thing behind the general relativity. So if space-time can be wrinkled by mass, it could be wrinkled to begin with. It could be, from the Big Bang itself. As a matter of fact, this is the measurement of the wrinkle. We just don't take it as a wrinkle. People are just saying that, okay, what's going on there? There has to be something. But look at this randomness, right? By the way, this is still by large flat. From the darkest to the brightest, to the most dense to the least dense space. It's the difference is less than 1%, something like that. So it's by and large very flat on a large scale. But the small wrinkles, just like I showed in the last video to the kids on that reflector thing, it's locally present. And that is basically the space-time, the dark matter. And how do we measure that? We can't. We can't measure that as a particle, right? Right now, a lot of experimentalists focus their energy on detecting dark matter particles or something. But that's a little preposterous to me, because if you have 5 times as much as dark matter, and and dark matter certainly react with gravity, right? Shouldn't dark matter just crunch up? Obviously, dark matter does not react to gravity. They just exert some sort of gravity to something else, right? If all the dark matter in the universe were somewhat like ordinary matters, then they can react, they gravitate toward one another, then dark matter is going to crunch up into black holes, like giant, supergiant black holes, and that we should be able to measure. But then all the black holes we do measure and we do find is far from not enough to account for all the dark matters, right? So that's a misleading thought on the dark matter front. They act like ordinary matter in some way. They don't. We already know that they don't. We know that they're not particles and things like that. It just doesn't make sense. So why can't we just think of it as what it is, a wrinkle in the space-time that was left there from, I don't know, last time everything was apart? It's like taking a piece of paper and then roll it up into a little ball, toss it, and then after you stretch it, there's going to be a wrinkle on it. So I don't know, I don't understand why that would be too hard to imagine, right? So I think let's get rid of that. That's what it is, just dark matter. And I think if we can accept that, then we can open up a lot of more ways to look at things. Now, is it completely not measurable? Not necessarily, because we did measure the gravitational waves, right? We do see this band of space-time on a more significant level, right? And to measure dark matter, I'd imagine we have to devise some sort of experiment in that front to see whether things change. Exactly how, I don't have any thoughts right now, but for example, if we use the same instrument as Earth goes through, we just record that instrument, record the variation in distance, maybe we can find something, right? Maybe we're gliding through this dark matter that we don't even know, we can't detect because we're not part of it, but then it does show up on very sensitive gravitational wave instruments, and that can really take the measurements, maybe say, this year and next year at the same time, and then the year after. There's going to be a variation at the same place without everything else, without any other disturbance. Well, first of all, we have to eliminate all the gravitational waves that we receive from the the colliding black holes or something. But there might be a way to measure it. Just we don't have it right now. But there certainly is not out of imagination for somebody to devise some sort of experiment to confirm that. And that reminds me of about 120 years ago, or just right before Einstein came up with the special theory, that people believed that there was ether, right? Maybe ether wasn't that preposterous of an idea, right? It just didn't behave the way that we expected it to behave. It's not the same as like an ocean of water or something that a ship is trying to glide through. Ether is completely something else. It's a 4-dimensional space-time, right? And it actually does not conflict with any sort of discovery and physical laws that we have. Okay, so the pros of having this explanation for dark matter and dark energy is that we give space-time its own physical property, right? We can have measurable, we can take measurements, like these kind of surveys can give some measurements, and then I think people are actively measuring the dark energy strength and then how fast we're accelerating in expansion. So those can be fit into mathematical models, right? So mathematically we can model them. And it's not too hard. It's it's just similar to material science. Okay, and then the pros is also that we don't need to introduce new special particles, dark matter, energy particles, things like that. So we don't need to introduce those to complicate things. And the explanation doesn't seem to contradict any sort of observations so far, right? Obviously, I don't know everything, but there could be something that contradicts with this kind of explanation. Okay, so these are the pros to have. Some implications, so we need to work on reconciliation with the standard model. People still, thinking that everything is made of particles, and they have that. And then this is actually maybe the space-time is Higgs field equivalence. Sort of find something in that area to fit it in. I'm not sure. And also, we can actually possibly find out the actual size of the universe beyond the observable universe. How do we do that? Like I said, if we can measure out the curvature, right, then we would know how big the universe is as a four-dimensional sphere or whatever, right? So that's how we can find out. And with that, we can also possibly define time with a spatial equivalence, right? So if we have a 4D sphere with a diameter of a certain size, and then we know that time has existed for 13.8 billion years, or whatever it is, then we can draw some sort of equivalence between those. So make time resembling more of a spatial dimension. Okay, so a few thoughts. These are just results of my sort of mental experiments. So I stand on the shoulders of giants, of those people in the community making all the measurements, making all the discoveries, and then I just dream about the questions that everybody else is thinking, right? But then I don't have to fight their fights. They have other considerations in their lives. So it may or may not be the big, lead to the big revelation of physics. I don't really care if it does. I think, just give out a way of thinking. So Eric Weinstein recently came out to reveal his theory that he worked on for however decades, and then he thinks that he's outside of the theoretical physics community, so he may not be welcomed or this and that, or the theory has special meaning and all that. I watched his lecture, and it's really hard to understand everything, right? So I'm trying to study his thoughts, but he is focusing on why something came out of nothing or something. I think that's a big question, but that's, I don't know, that's not. But anyway, I don't see myself being, in his shoes, that I'm afraid to reveal my thoughts. And I've seen other people revealing their understanding. So I recently watched a video. Somebody has another theory about dark energy. Basically, he's thinking that, the universe is sort of like the shotgun pellets that's spreading in directions. But since we're traveling really fast in one direction that we don't notice, and everything else is in the same frame, that we don't understand what's going on in that direction. It's plausible, but there's no way to confirm that, or maybe he has some way to confirm that. Those are really good thoughts. I can't say that he's wrong, more so than I am, right? Okay, I guess that's it. Welcome any sort of comment below. And today is June 10th, 2020, 6/10/2020. Okay, so hopefully, we can get some understanding, deeper understanding. I'm going to keep thinking about it. I'm going to try to think that where I could be wrong or something, and then maybe I do some more math behind it to come up with some sort of formula to describe what I've discovered or what I've thought up. Science Photo Library, I borrowed that. Okay, thank you.